Perfect. All right, so we're going to talk about graph databases today. So my name is Jennifer Reif. My contact information is there in the lower left-hand side. It'll also be on the next slide and the last slide too. So if you think of questions, we do have a relatively short amount of time today. It's not the downside is we don't have like an in-person event where you can just catch me in the hall or another day of the conference or whatever. But on the bright side, everything is super digital, and I am always available online. So feel free to reach out to me if you think of questions down the road about graphs, Neo4j, tech. I'm happy to talk all those geeky sorts of things if you think of something later on. So a bit of background. Darren already kind of gave a little bit of this, but I'm a developer and advocate at Neo4j, have been for the last few years, and I like learning, which is probably a good thing. And most of us in the tech industry probably do too, right? And then whatever I've learned, I like sharing that in a variety of different ways, whether that's through blogging or a conference or meetup or virtual event speaking. I do have hobbies outside of work, but most of them boil down to the fact that I'm a geek at heart, if you can't tell from the picture I put up there. And then my contact info there. So let's dive right into our content. So everything really is about data, if you think about it. Everything's built on data. Our businesses, our industries, our governments, people, our understanding of the world. Data is how we learn, right? From school age, from toddlers, from young children, all the way to adulthood and beyond. We take everything into account. We take our experiences. We take what we see, what we hear, our interactions with other people, and those are data points along our life journey, right? So a lot of times we learn something through trial and error. We try it a few times and we figure out what not to do. And then we figure out, oh, this works. Okay. We ask a lot of questions and we accumulate that data over time and make hopefully better and better decisions as we go. So even our relationships with friends and family and so on, we accumulate those data points. I've been doing a little bit of reading the last several weeks, I guess, on this book, Domain Driven Design. If you're probably Java developers, maybe some other types of developers, you may have read this or may have at least come across it. I'm just now getting to it, but it's a really good book, and it talks about how your data domain experts, your developers, your business folks, etc., when you have a mutual understanding of a domain of your data and of your model and the concepts, you build better software, you build better businesses, you build better projects, etc. You usually do this through some sort of iterations, which is how probably a lot of us code. And by understanding the data, that gives you a better understanding of the result, of the solution, of what your customers want, etc., no matter what you're trying to build. So on the end game there, you get a better product, you get minimum functionality. You're not going to build a whole lot of extraneous things because you understand what's in the data and what you need to get out of it. And it also helps to sanity check your code against kind of the model and the understanding of the data you're sucking into it, right? So it's a really good book. I do recommend it. I'm not all the way through it yet, probably about halfway or so. And it's just kind of a on the side project kind of reading I've been doing, but I find this really interesting and something that fits really well with databases and data as a whole. So you might be wondering, hey, I know all about relational databases. I might have heard or worked with a little bit of, document databases, MongoDB, maybe some others. Why in the world do we need another database, right? Do I really need to add another one to my list? So relational databases, kind of the goal here is we're going to look at a few different types and kind of figure out the goals and the pros and cons of each one of those. So with relational databases, the goal really is to assemble data into meaningful sets. Remember, relational databases came out somewhere around the 1970s. So they've been out for a long while, but in computer history, it was a much different time, right? You had different storage goals, you had different programming capabilities, and the environments look totally different, right? So the pros of relational database, still to this day, is you get slices of data you can easily assemble with queries. It also handles good data integrity, so you don't end up with kind of mismatched data or out of sync data, if you will, and unique rows, and you get low data duplication here. So they try to create unique kind of objects, if you will, of data, and you then assemble kind of aggregates or groups of this data through queries. The downside with this is that all relationships you need to assemble with joins. And that's if you follow the normal forms, the first, second, third, and so on, normal forms of good data normalization. If you denormalize your data, then you don't have to do as many joins, but that causes other problems. So if you have good normalization, you're going to have to assemble all of those data kind of views, if you will, using SQL and joins. Joins are constructed from human knowledge. Either you've documented how the relationships exist in the database so that you can query across those, or you have those foreign keys in the database that then you can kind of make, okay, I need to join this table with this table because we have a foreign key relationship here. But again, you're looking at human knowledge that's constructing those relationships. So this is not a serious one, but I found this image on Google and I thought it was hilarious. This is an example of an entity relationship diagram, or an ERD. And this is a massive one. I've seen ones this large. In fact, my former company, there was one that took up an entire 2 or 3 cubicle walls, stretched full, big, massive paper that they stretched it all across. But hopefully you don't have that many ERDs that are that large. But still, I found this really funny, this massive entity relationship diagram of all the tables and their relationships, and they put Pac-Man on it, which I thought was hilarious. I do have a source for where I got that too. I'm happy to share that. But I found that off Google and thought it was funny. So, okay. Let's talk a little bit about NoSQL or document databases now. The goal here was to kind of avoid assembling all those individual bits by grouping related info together. So the good thing with these types of databases is you can handle a variety of unstructured data more readily. So you can deal with kind of missing values, or kind of objects that are a little bit misshapen, if you will, and so on. That also groups related info into a single place. If you group everything into a document, anything that's connected, then you're able to just retrieve that document and get all the information you need. The downside here, well, you are going to take up more storage because you're storing more data in a single object, right? And if you don't need all that data when you retrieve it, you're going to get kind of a bloated object, if you will. But it is designed to avoid joins and SQL. That's a pro as well as a con. So you don't have to mess with joins and SQL. And that was kind of one of their design goals. That's why it was called a NoSQL database. But the other downside is that it's going to make your aggregation operations, anything when you do have to do a join or kind of a lookup operation across documents, that does make that very cumbersome because, again, it's not optimized for that. It's optimized to pull an entire object group back together. So when you have to go out and follow those joins and pull back related stuff, it's not really optimized to do that as well. Okay, so an example of this is looks like maybe a customer or an employee here. And we have kind of linked social media accounts. As you can see, you also have linked departments that I'm talking about the document mostly on the left side of the screenshot there. And then we have, a couple other documents on the right side. Notice that they don't have social media accounts that are linked. Their departments might be a little bit different, and so on. Again, that's kind of that misshapen object, if you will, where they don't all have to match. They don't all have to be uniform like you would have to in a relational database. And then you have kind of these nested joins where the social media accounts for Tom Johnson there are actually built and baked into his document there. So again, you're not having to do that join, but if you wanted to find out maybe if his colleague shares, or if his, let's say, spouse or partner shares a social media account, that would be very tricky to do because you'd have to query more than one user. You'd have to look for the linked social media accounts and so on. So can be pretty cumbersome depending on what type of queries you're doing, but designed and optimized for something else entirely differently than relational databases. Okay, so graph databases kind of came into play. The goal here was kind of to mediate the pros and cons of the other two. So to try to get the best of both worlds. Obviously, it's not going to fill every gap, but the attempt here was to take the bad things on SQL and the bad things on relational databases and the bad things on document databases and try to improve them and make them easier in a graph database model. So the good things about graph databases is your relationships are going to be stored with the related entities, no assembly required. So you don't have to do joins, you don't have to do lookup values and so on. It's to make the join operations easy and even visual, which we'll take a look at here in a bit. The downsides here is you are going to store relationships inside the database. So that does require a little bit of extra write operations every time you insert something. You're not just inserting the data objects itself, you're inserting any relationships that connect it. And there is a different mentality when you talk about modeling, querying, etc. So I find that kind of takes a little bit of an adjustment if you've come from especially a relational background or even a document background too. Okay, so this is kind of an example of what graph looks like. And so this is one off of Neo4j's website. It's one actually I created for Neo4j's website a couple years ago, but we have people that are in blue. We have the things that they might like, the technologies they might like in green, and then we have companies they might work for in red. And you can kind of see if we pull some of this apart, we can start to better understand the data because of the relationships that are connecting it. For instance, you can tell that I created this graph because I'm very well connected in the graph. My node there is in the middle. You can see I have a lot of relationships going to other things. So me being the creator of this, I'm kind of the central grouping around this. But there are several other people in there as well that seem pretty well connected, several companies that are well connected. ABC company in red and XYZ company have a couple of different employees, and there's things that are likes. Obviously, graph kind of comes out on the top and so on. So we can understand more about the network, understand more about people and the companies by the people they employ or the technologies the person might like or who they might work with on a day basis, etc. Okay, so do you have to pick just one type of database? No, you do not. It's called Polyglot Persistence, which is using multiple persistent strategies, each serving a different need. So somebody can use a relational database for this project, somebody can use a graph database for this project, somebody can use a NoSQL database for this project. And it's called kind of using the right tool for the job, right? So picking the right technology that matches what you're trying to do and the solution you need to build. So you end up with then multiple solutions and you end up with this polyglot persistence. Nothing wrong or bad about that. There's a lot of customers and companies out there that do this. And it really just means picking the solution to fit your project. Okay. So what is actually a graph? We kind of know where it fits in the database market maybe, and how it kind of came to be. But what actually is it? How do I piece it together? So we'll go back a little bit. Graph history is much, much older than the technology of this last decade or two. And it started with Leonard Euler back in the 1700s. There was a math problem that he was trying to solve. You had in the city of Königsberg, Prussia at the time, there were 7 bridges that connected 4 land masses. And he wanted to see if he could start in one place, cross all bridges, and come back to his starting point without duplicating. So without crossing the same bridge twice and so on. This problem is actually not solvable. However, the study and the math that he put behind it founded graph theory all the way back in the 1700s, which you see kind of in the image on the right-hand side, that the technology was then based on in the last decade or two. So this problem is much, much older than technology. It's just we've built technologies around this mathematical theory now. So graph databases started about 2010. Neo4j was the first on the scene for graph databases. There are kind of similar types of databases that were out previously and so on, but the first initial graph database coined technology was back in 2010. And as most technologies, it arose from a solution need. There wasn't a current solution for what they were trying to do in the technology space, looking for a better way to handle certain problems. So the existing technologies just didn't do what they needed them to do as easily as they wanted it to do them. So they built their own and they started their own, right? And so that's where most technologies of today have come from. All right, so what do graph databases solve? What are the kind of the use cases? I have an example here of the Northwind Data Set. If you've done a whole lot of database work, you may have come across this data set before, but it's kind of a typical sales system. So you have products, you have customers, you have orders, you have the employees that sell those products, and so on. So for a product use case, it's going to document the path, not just the data that you're getting. So kind of the more relational database, to some degree document database, it doesn't really give you the path of how something ended up that way, right? It's going to give you all those links, but then you have to construct that path yourself. Graph databases kind of store that path, and so therefore you can see that path without having to construct it yourself. It helps you answer how and why something is to be, especially if you have historical data in there or kind of tracing back through. So how do we get from point A to point B? Well, here's our normal route, but if normal route is closed, here would be the alternate routes we use, etc. Helps you understand connections. We'll talk a little bit more about that as we go on. Finding alternates or impacts. So for instance, if a truck is down on my shipping company, that means that it's going to impact the deliveries that I can get out or the number of deliveries I can get out that week, right? So it helps you produce better assumptions and make better decisions based on the data you have. So the thing that I really like to say is that graphs add context and meaning to your data. You're not just going to get the point to point, this is connected to this, but it's going to help you understand how they are connected. For instance, we have two people here, a technology and a company. So a subset of the graph image I showed earlier. And now we can kind of understand Jennifer a little bit better because we know not only is she connected to Neo4j company? Maybe she just likes their technology. Maybe she follows them on Twitter. Maybe she whatever. No, she actually works for this company. There's a vested interest there, right? She is friends with this person named Michael since a particular date. So you can quantify, okay, maybe this person might be a good person to get a reference from because they've known each other for years, instead of something like they just met in a coffee shop or they happen to share the same Uber or they happen to go to the same conference. No, we're actually saying this person is friends with this other person. There's a deeper connection there than just they're connected. And then same thing with the technology, all kinds of different things that person could be connected with graphs. And yet, no, we understand that this person likes graphs. There's a vested interest there. Okay. All right, so a couple of misconceptions about Neo4j that I often hear, so things that I just want to kind of toss out there, is Neo4j graph database is actually a database. It's a physical storage of data. It's not just an analysis tool. It's not just a visualization. You are actually storing data to disk. It can be used as a system of record. One that I hear a lot is, well, it's just an analytics. It's an OLAP workload, right? And Neo4j is not. It can be system of record, source of truth database. It can, in fact, the initial use case was transactional. And like any technology, it's not a silver bullet. It's not going to solve everything and do everything for you. There are things it does not do well, and I'm happy to go into that or talk about that later on. Or if you have questions about that, feel free to ping me. But there are some things that it doesn't handle super well, just like any technology, right? And then there are things that it does super well. Okay, so let's talk a little bit about the graph structure, how we put a graph together. Neo4j graph databases, even in general, are known for being what they call whiteboard friendly. This basically just means it's easy to design and model a direct representation of your data. So that sounds like a lot of fluffy words, but let's actually look at this. If I were to draw a data model, typically when you sit down with a new project or you're looking at a new domain, you kind of go to the whiteboard or a piece of paper and you sketch it out, right? Most of us hopefully do that. I know at least I do. But so we have our orders and our products. We have suppliers that supply certain products. Products are kind of grouped into categories, if you will. And you have employees who kind of sell the orders. So you have sales folks, and then employees report to other employees, right? Managers and so on. So you could sketch that out. You probably would end up with something similar to this. And then when you actually store that in the graph, you get something like this. So notice how actually pretty much the same, besides for some added color and, styling, CSS styling that goes on. It looks exactly the same as what we just drew on the whiteboard. And so that's the whole point graphs and being whiteboard friendly. The model that you draw on the whiteboard is pretty close, if not exactly the same, as what's actually going to get stored in the database itself. So graph components, there's a few different basically pieces of the model, if you will. So some terms you'll want to know about. The first is node, or if you're familiar with the mathematical term, it's vertex. So the mathematical version of graph theory, if you will. So we call them nodes and relationships as our two main entities. In mathematics or graph theory, you'll hear them referred to as vertex and edges. So we have nodes and we have relationships. Nodes represent objects or entities. So for instance, an order, a product, a person, a car, etc. You can label them. So for instance, I've taken the two nodes and I've labeled these or categorized them into orders and products here. Again, you could add lots of different labels depending on what kind of categories. Think of almost, if you're familiar with the relational background, think almost of table names as kind of being your labels. You can also have properties or kind of metadata on those nodes. So for instance, an order, you might have an order ID and a total that the order comes up to. You would have a product ID probably and a product name. And then the employee maybe who sold the order, you would have an ID when they started at the company and their role or job title or contact information or so on. But these are properties, metadata about the entity itself. Relationships are a separate entity in the graph because we're making them equal importance to the data objects themselves, unlike kind of other types of databases. So we're elevating relationships as being, you have your nodes, you have your relationships, they're equal parts in the graph. You need both in order to make sense of data. Relationships have to have a type and you have to have a direction. So for instance, you can see we have our typical order, product, employee, but now we have connections between them. So now we understand how order and product are related. An order contains a product. An employee sold an order. So they were the salesperson there involved. So that's the type is the sold or contains. So it tells you basically, it's almost like a relationship label, if you will. And it just categorizes or helps you understand the context between the two entities you're connecting. And you do have to have a direction. Now, note this is a required direction for when you store the data in the database. When you actually query it out of the database, you can query it in either direction. What we call bidirectional. It's just when you store it, you have to specify a direction. You can also add properties to relationships. So for instance, the employee sold a particular order. The order might have gotten put in on a particular date. The employee might get a commission off of that order, and so on. So it doesn't really fit to create a separate entity here. Here, when they sell the order that goes through on a particular date, they get a certain commission off of it. So the relationship then has those properties. Nodes can share multiple relationships. So for instance, an employee might have gone out and created the initial order or the sale documentation. The order has a particular contact. So if we were trying to figure out, okay, for a particular order, who would I contact about that to get the information or so on? And then an employee sold that particular order. So again, you can have multiple different types of relationships. They can be in any type of direction and so on that you need to. Okay, labels. It's kind of a group of nodes, kind of like a category. For instance, we have several entities here that we're all kind of labeling or categorizing as persons. We could also add additional labels if we wanted to. So the general category of persons, we might also have some persons in there that are employees. We might also have some that are customers. And notice we have one entity in the middle who happens to both be an employee and a customer. As my former company, of course, I would be labeled a person or a user, if you will. And then I was an employee, so I would have had that little employee. I would have been on their employees table. But then I also purchased a couple of swag items through their store. So therefore, I was also a customer because I'd made a purchase from that company. So then I would be labeled as all three. Be a person, I would also be an employee, and I would also be a customer. And you can absolutely add those additional labels in there for additional categories. Okay, Properties are key value pairs. They're going to be associated with a node and or relationship, as we've kind of already talked about. And it's kind of like a variable name and value. So in programming, that seems very familiar concept to us. And so this is an easy way I like to think of it. So you can kind of see some examples. I've taken just individual properties, lots of different data types, lots of different formats, and you can assign those to nodes and or relationships. All right, let's talk a little bit about the query language. So if we were looking at SQL versus Cipher, now granted, this is a select purpose query here. So I've taken kind of a standard query that we would use joins on. If you weren't doing joins, the SQL query would be super simple. But that kind of defeats the purpose of graph, right? Graph, you want to have those relationships. You want to query those relationships. So when you start looking at joins in SQL, if I were to look at, okay, what are the products on a particular order? That's a many-to-many relationship, right? An order can have multiple products on it, and a product can belong to multiple different orders, right? So most of the time when you have many-to-many relationships, you create this associative entity or this join table or lookup table, however you want to term it, called something like ordered product. And you go across order, you're going to find the products that are linked with that order, and then you're going to go over and actually get the product name and product information that's connected there. So that's why we have the select on the particular fields we want to bring back from the order table. Then we need to do a left join on the ordered product table, and then do another left join on the product table to get the end results and bring that information back. In Cipher, because that relationship is already built in, we just match the order, and then we want to find the products that it contains, and we return all of those entities. So the Cipher does look much shorter, much more efficient, much simpler. That's because graphs are designed for this sort of query, where relational databases aren't maybe designed as much for that. They're designed to assemble those pieces together. Okay. So Cipher query language is both functional as well as visual. It's based on ASCII art, which is why it looks kind of cute and fun. But don't be fooled. It's pretty powerful too. It's a declarative query language, and it focuses on what to retrieve, not how to retrieve it. So you tell it, this is what I want you to look for, and it will figure out the best way to do that, to go about that through the engine. So if I were to look for or create this pattern, Jennifer works for Neo4j, this is the query or the statement that I would use to do that. So I would use the create keyword, which is kind of like insert in SQL. And then I need to create two nodes, right? Two entities, Jennifer, Neo4j, and a relationship between them. So our two nodes are going to be surrounded by parentheses. And if you bring those parentheses together, they form a circle, which is exactly how we draw it in the visualization, draw the node in the visualization. So again, based on ASCII art, it's supposed to look as much as it is functional. And then we have our other node for Neo4j, again, enclosed in parentheses. And we have that relationship in the middle. You can kind of see the arrow and the kind of brackets around the relationship type of works for, which again looks very similar to the way the relationship is drawn or visualized in the image right above it. Next, inside our nodes, we have our labels. So these are the categories we want to put the nodes into. So I'm categorizing Jennifer as a person. I'm categorizing Neo4j as a company. And then I would have a property within that, which is inside curly braces. So I have a key value pair, name Jennifer, company name Neo4j. And then I can create that in the database. Now, if I create that in the database, how do I query that back out? How do I read that basically? You can use a match keyword, just kind of like select in SQL. I want to look for a person node with a name of Jennifer. I know she works for somebody, some company, right? But maybe I don't know who. So I can actually take the parentheses on the other side. I can put in a variable there of whom, and I can just return everything the database has on whom. So it'll return all the details, the properties, and so on about that entity itself. Of course, we know, as we can see from our visualization and from the query that we inserted just before, that it's going to return the information about Neo4j because we know that's who is on the other side of that works for relationship from Jennifer. Okay, so just kind of an overview of Cipher. Nodes are going to be encompassed in parentheses. You can have variables that you can assign that you can reference them later in queries. You'll have a label potentially, and then you can also have property keys and values inside curly braces. Relationships are going to kind of have an arrow type format with brackets. You can also have variables for relationship types that you can reference them later on in the query, and you can have property keys and values inside curly braces for relationships as well. Remember, they're separate types of entities, but very similar to nodes as well there. So Cipher then, as an oversimplification, is really just looking for patterns of nodes relationships. So node, relationship, node, however many hops you want to do, Cipher is basically just doing pattern matching. Now, again, oversimplification, there's lots of caveats and complex things you can do with Cipher. But if you just remember when Cipher gets like really complex looking, remember, I'm just looking for patterns. What type of pattern is it trying to ask? Okay, a quick hit on building applications with Neo4j. We do have lots of drivers with lots of different languages supported. There's lots of plugins and extensions and libraries out there. One thing that I really find cool about Neo4j is there's lots of things you can plug it into. So we have an APOC utility library that does a lot of sorts of import and text modification and reading from other types of databases and so on. We have a graph data science library. We have a GraphQL integration, if you will, that'll help you build a GraphQL API, on top of Neo4j. Then we have other things, all sorts of things there as well. As far as integrations and frameworks you might want to connect to, things like Spring, Micronaut, Quarkus, all of that works with Neo4j. And then if you are using specific tools in your tool chain right now, there are quite a few of them that Neo4j already has worked with or has an integration or a connector to, things like Kettle, Spark, Power BI, JDBC, and so many more. There's a long, long list. So if you're looking for something in particular, feel free to go out to Google and type in X technology or X tool and Neo4j, and there's likely something somewhere out there that's been built for that. All right, let's look at the actual database, see what this looks like, and run some queries. So I'm going to switch over to my browser here. And oh, we do have some stuff in the chat. I'll just take a quick gander. Lots of highs, which I could not see. Okay. Is there any issue if there's a cycle in the graph? Okay. That's a very good question. So sometimes, sometimes there is. With Cipher, it avoids going over the same path twice. So if you have, let's say, two nodes and you have two relationships, it will only traverse unique paths between them. So that means that you'll go from node A over to B using relationship 1, and then you'll go from node A to B using relationship 2. And that's it. It's done. It kind of keeps a stash in memory of, hey, I've already read this pattern. I've already read this pattern. This is not new to me. Where it can potentially get you into trouble is where you have tons and tons and tons and tons of relationships between the same entities. So for instance, if you have, let's say, a triangle, 3 nodes, and you've got maybe 15 relationships between each one of them, you're going to be traversing between those same 2 nodes 15 or more times. And of course, so if you have, thousands or millions of different relationship types, that is going to be a problem. Cipher will keep track of those for you so it doesn't go over the same path twice. But there might be certain tools that aren't as rigorous that when you connect to it. And then, of course, if you have tons and tons of relationships between entities, then that could be a problem. However, if you have that many relationships between the same entities, more than likely there's something wrong or something that could be better formatted in the data model itself. So there's probably a better way to model it so that you don't have those problems. That's usually what we find is those types of problems crop up when the model really could be improved, and there's better ways to kind of diagram that data model. Yeah, okay. let me catch up here. Good question, though. Let's see, is there a way to create a constraint? Yes, there is. The type of constraint you are asking for, though, is more like a relationship direction. So, for example, a person can work for a company, but never the other way around. So a company couldn't work for a person. There currently is not a way to specify relationship direction in a constraint. We do have relationship constraints. Right now, it's a unique constraint. So you can't have, let's say, more than one type of relationship type, maybe between entities, or you can specify, hey, let's say a commission that somebody gets off of an order, you couldn't have more than one commission listed for an order or something like that. So there are some relationship constraints, but not any that I know of that are exactly what you're asking there, which is based on relationship direction. If you look at our Cipher manual, our documentation, it'll list all the different types of constraints you can have on nodes and relationships. We do typically, when we have a new release of Neo4j, add additional indexes and constraints for nodes and relationships. So do keep kind of an eye out. That may be something that is coming that I'm not aware of. We'll collect data from multiple sources, news sites, and in some sources, we have a data set which have their own relations. Other sources are tagged or labeled. In SQL world, we'd run some queries and results are shown. They're mostly what we expect. How can Neo4j be more of an advantage to adopt it in our project? Okay, good question. Probably a longer question. I'll try to do my best to keep this relatively short so I can jump into the demo. But so you're pulling in from multiple sources. Some sources, you have your own relationships. Other sources are tagged or labeled. So where this would be super helpful is you're pulling in all this data from lots of different sites. You might want to, they have their own relationships, sure, but you might want some sort of entity resolution, if you will. So figuring out, okay, I have entity A over here, I have entity B over here, I have entity C over here. Are they actually all the same entity? Is this the same article that's been published multiple places? Is this the same news story that's being reported in different channels? And you can do some sort of entity resolution to figure out, okay, we actually do have the same entity and these 6 different news sources have reported on it. And so then that helps you better understand at that point, if you do sorts of things like that, that helps you better understand, okay, we have, X topic that was reported on 6 different media outlets. We have Y topic that was reported on by 15 different media outlets. And these are the types of views that they got. Therefore, we can kind of make the decision that, hey, this type of topic or these types of news sources get better viewership, or people are more interested in these stories than they are these types of stories. So when you start bringing in lots of different data, that's where I see Graph as being super helpful, because you're pulling in all this data that seems totally unrelated. But when you dump it into a graph, you're creating those relationships without even realizing it. That data is already connected, and you can take those commonalities and figure out, oh, I have articles with the same title, or I have articles that have the same exact tags, or I have articles that maybe are from the same authors. And then all of a sudden, those relationships that you didn't even know existed before are popping up in your graph. And so then you find these hidden relationships that you didn't know existed before. And all of a sudden that turns this data from maybe 5 different data sources into a knowledge graph, or into information that you can utilize in your business, or help you understand the world better. Because not only now do you understand about topic A, you're able to link topic A, what you know in topic A, with something that's a totally new topic. And now you have a better understanding for this new topic because you took something from A that connected and helped you understand topic B better. So, I mean, that's how we learn, right? We take something that we understand really well. When we learn something new, then we relate it back to what we already know. And that helps us grow our knowledge and improve our decisions, right? So this is really what Graph is good at. And it's really cool to see that information kind of come alive. Not as short of an answer as I was hoping to get there. I apologize for that. Do indexes work in a similar fashion? Compound index is also possible. Yes. So indexes do work similarly in the fact that they will help you kind of optimize or improve the speed of return results. The difference is that most of the time in SQL and relational databases, you are indexing the lookups, the lookup values. What you're doing in Neo4j is you're indexing a starting point for your data. So for instance, if I'm looking for a person of Jennifer in my graph, it'll kind of know, okay, I need to look for persons. So I need to look at this group of nodes that are labeled person. I know there's a name property, and I know it has a name of or a value of Jennifer. So I can kind of filter out and narrow down and get to my starting point in the graph, and then I can follow the relationships out from there. Where if you didn't have an index, it would need to basically search the entire database for that. Same thing happens in SQL, relational databases. If you don't have an index defined, it's going to scan the whole table in every field and so on for that value you're looking for. Indexes help you do that a little bit faster. But again, you're indexing lookup values in a relational database. You're indexing a starting point for your graph traversal in graphs. Compound indexes are possible. I can send out a link for the documentation to show you exactly what's there and all that, but you can do that. Is it write friendly? Yes, it is. So I did mention that you're going to sacrifice a little bit of write speed in a graph database, but it's pretty minuscule, to be honest. Your reads are going to be so fast, and your writes are going to be a little bit slower than, for instance, if you were to pick relational database or document database. Document database, your objects are going to be bigger. Your writes are, if you had a lot of joins and connections you were inserting, basically, then that write would be slow as well. But if you're just inserting documents, it creates the whole object. You don't have to worry about connections or relationships there. Where when you create in a graph, you are potentially creating lots of relationships along with it that connect other entities. So you're going to gain a lot in reads because you're not having to assemble those joins when you write the read query, right? But when you actually write to the database, it's going to be just slightly more overhead than you would see for relational and document. Hopefully that answers your question. If not, let me know if you want to know more details. I can do my best to point you in the right direction there. Data sharding. Yes, we do data sharding. Scaling. We have both vertical and horizontal options for scaling. So you can size up your instance size, basically your storage, your RAM, and the heap. The biggest things that are graph dependent are going to be your RAM and your heap. Those are the two big things that you want to make sure you have quite a bit of when you're dealing with a graph database. And then also, if you want to horizontally scale, we have what's called Fabric, which is basically sharding. And that separates your graph into multiple different machines, basically. And you can query across those machines. The thing that's more complicated about graph is, again, you have those stored relationships. So you have to find decent points in your data model to kind of break that data up into different machines and then query across those. But by all means, we do support that. And horizontal scaling is possible there too. Okay, so I think I'm caught up on all the questions there. Let me go ahead and dive into the demo. Hopefully, this might help clarify or answer some additional questions as I move here. So I have some data loaded into a free cloud database version of Neo4j. And so I'm just going to call a procedure here that's going to show me the data model. Now, this is an APOC procedure. So I mentioned the APOC utility library. This is one that is super helpful. Our current built-in procedure that will return data model, it has a little bit of a bug in it. So I use this one to make sure it's cleaner, but we do have a built-in database procedure that does this too. All right, so we have a customer who purchased an order. That order orders a particular product, and that product is grouped as part of a category. We also have suppliers that will supply certain products. So this is kind of the data model that we're dealing with. And so let's just kind of start querying some things and exploring the data that we have. So let's see if we can find some products. And let's return some of our products. Let's just get a smattering of them. So we have products, grab product name. And we can see we've got a few different types out here. IPO coffee, which of course would be one of my favorites. I love coffee. You can see kind of some details that we have about this entity. So we've got a category ID linked to it. It's not discontinued. Woohoo. So that means they're still selling it. We have the product ID, product name. We have the quantity per unit. So they're selling 16 500-gram tins. It's probably more of a bulk, supplier to stores and that sort of thing, maybe. They have like a reorder level and a supplier ID and a unit price and the units in stock and the units on order. So they do have an order out for 10 additional units. And of course, we could kind of explore. There's a chocolate drink out here. There's some dried apples out here. There's lots of things I probably can't pronounce very well, so I won't butcher them. But raclette and camembert and there's some Perth pasties and so on. So there's lots of different types of products. We could kind of point and click around, but again, we're not really doing anything super graphy, right? We're not taking advantage of those relationships. So let's look for some products that belong to some categories. So part of category, and then let's just return some of these. Return everything. Okay, and I have to. Visualization doesn't like me today. So zoom out a little bit. And I'm kind of, now this is, it's a little bit of an eyesore, but I'm going to hopefully improve that. So I kind of just drag the visualization stuff so we can view these a little bit easier. Here, and this is just the visualization tool for the data that's actually in our database. There's other ways to go about retrieving this data. You can run queries from an application through a driver. You can use our natural language search tool called Bloom. And there's all sorts of other things. But so we have some dairy products out here. We have some meat and poultry products out here. We have some kind of my favorite category is confections. So you have desserts and candies and sweetbreads and so on. You've got some beverages and seafoods, and there's grains and cereals and condiments. We're going to kind of focus in on produce because there's not a whole lot of products kind of connected here, so might be a little bit more manageable for us today. So we've got apples, we have tofu. I'm not exactly sure how that's produce. Sauerkraut, again, I'm not sure that I would agree that that's produce. And then some other tofu, and then we have some dried pears, which again, a little bit more traditional. We've got dried apples and dried pears. That does kind of fit into the produce category for me. All right, so we have some different items here. Maybe we would want to find out a little bit more about those dried apples, for instance. So let's just see what all is connected to our dried apples product. So I'm actually to kind of copy this, and I'm going to just grab any other type of entity that's connected to this product. I'm actually going to remove the direction on the arrow too. And then let's see, product name, and we have our Manjimuk dried apples. And then, yeah, we're going to return everything. Let's see what we get. Okay, so we have some orders. I'm just going to grab an order ID for these. So we have some orders. So lots of orders for dried apples. Oh, we also have a supplier. Let's grab the company name for the supplier there. So it's supplied by G'day. And it's in the category of produce, of course, as we know. But this is kind of interesting. For instance, we're dealing with some supply chain issues. We don't see more than one supplier here. That might not be a good thing, right? Maybe we'd want to figure out, okay, are there any other suppliers of that particular product? So let's look specifically. Excuse me, can't talk. Supplies those Manjimuk apples, and let's see what we get here. Yes, in fact, we only have one supplier for these dried apples. Again, that doesn't sound too good, too promising. But let's see what we have, maybe who supplies produce in general, to see if maybe we might not be able to get Manjimuk dried apples. Maybe we can get another form of dried apples, or maybe we can get another dried fruit potentially. So let's look for, it's specifying here, let's go find out. We have a category of category name is, type produce. And then we have a relationship here. R1, part of category. So then supplies, okay, return everything. Okay. So here's what we get. We get produce, and let me kind of zoom out a little bit so it's a little bit easier to see. We have produce. We have the 5 products that belong to that produce category. And it looks like we only have one supplier that provides each one of those. So if we have a supplier that goes down, guess what? We've lost a product potentially, right? So let's kind of double check this a little bit and see if we lose a supplier, for instance, what else will we lose along with it? Do they supply other things as well? So let's look for the category produce. Let's just kind of return this a different way. Let's look for the company name. Company name. And collect the product name that they have. So you don't have to return kind of this graph visualization. You can also return a table version of this, which is what I've done here. So I have the company name, and then I have a list potentially of products that that company supplies. So you can see for the category of produce, the only produce that G'day provides is this Manjamup dried apples. So again, if we're out of Manjamup dried apples, then we don't have anybody else to fall back on if G'day doesn't have any more stock, right? That's probably not too good. Now, what happens if G'day goes out of business tomorrow, or let's say something gets shut down and they have no way to get products from their plants? What else could we potentially lose from them? And are there any other suppliers that we might find some overlap that we could at least shortchange something similar, right? So we're going to take this and we're going to remove this because we want to look for supplier who supplies products that are part of a category. And then we're going to take our company name, our supplier's company name as the company, and then we're going to collect the categories that they supply into a list. So distinct c.category name as categories where produce is in that list of categories. So we want to find all of our produce suppliers basically and figure out what all they supply as well. And then we're going to return the company and we're going to return the categories list. So here we get, let's go look down here at our G'day that we've been looking at supplier. They not only supply produce, that one dried apples of product of produce, they also supply some meat and poultry products, some grains and cereal products. Now we could kind of look and say, okay, if this company goes under or they're not able to ship things, do we have other companies that might be able to provide these items or similar items in its place? So we can see, okay, grains and cereals. We do have this Plutzer that can also do grains and cereals. We have meat and poultry. Looks like they can also do meat and poultry. They can also do produce. We also have meat and poultry and produce coming from Tokyo Traders. And we have produce that could come from Mayumi's and from Grandma Kelly's homestead. So again, we have some alternates here. We may not be able to get the exact product in, but if we're having trouble getting any type of fruit in, maybe we could at least substitute with some similar products until our G'day supplier comes back online. So again, some options there. Now, let's say we have a new product that's come on the market, a new produce product, and we want to find out who should we market this to first. We know we have customers. Who are our customers that buy the most produce? So we have customer, and they will purchase particular orders, and those orders contain order particular product, and then those products are part of a particular category. So we have category here, and we want that category to be, you guessed it, produce. Produce, like that. And so then we want to bring back our individual customers. cu dot customer name. And then we want to sum up the items that they ordered. And so we want the orders, the R2 dot quantity. So the quantity of the items in a particular order of that product as products. Order by products. And technically that's produce products there in descending order. What did I do wrong? Property key is not in the database. Oh, this is instead of customer name, I think it's like contact name or something. Yeah, that looks right. Okay. All right. So we have this person up here who has ordered 353 produce products. And then we have kind of these folks down here that still have ordered quite a few. So maybe if we have a new produce product, a new, fruit or vegetable item we'd want to offer, maybe we want to send out a notification or an advertisement or coupons to the people who order the most. Or maybe if we want to encourage our produce to sell better, we would send out notifications and coupons to those who buy the least, and it might encourage them to purchase more produce products, right? So again, a couple of different strategies we could apply here, but looking at the graph data from a totally different perspective, rather than suppliers and what happens if our supply chain is broken or something happens to it, impacted. Let's look at our customers. How can we better approach marketing to them or advertising to them or getting the word of our products out there more? Okay, so with that, we are like right on time here. So let me pop back over. I'll check if there's any more questions here. Documentation for the APIs and SDK. Yep, I can send out documentation. Okay, are there cool graph theory math operations you can do as well, measuring connectedness of a node? Yes, there are. So Tim's question asking, this is more... Probably you're thinking more of like graph algorithms. So things like connectedness would be, I'm drawing a complete blank on what the graph algorithms are called. But there's lots of them out there. You can check out our graph data science library. And there's some sandboxes and things you can play with that library for free. And there's lots of things like link prediction and I'm just drawing a complete blank on the types of algorithms and some of the algorithm names. Louvain algorithm and that's going to bug me now. But anyway, there's tons of information out there for that. And strongly connected components, that's one. Thank you. And there's weakly connected components along with that too. And then also we do have some built-in functions, things like shortest path and some other path metrics that are built into Cipher. So you can do some of those things through Cipher as well, but the bulk of those operations, especially on a large scale, are going to be in the Graph Data Science library. So if you're interested in that, feel free to check out our Graph Data Science library for that. There's tons of options there, and it's really cool, the information that you can pull from graphs using those sorts of things. Okay, so with that, I'm going to wrap up and give you guys links to stuff. If you want to spin up a free cloud database that's run and hosted by Neo4j, and it is permanently free, you can spin it up as long as you want. It does auto pause after a few days, but you just resume it and kick it back on again. And it's, again, totally free for its life. And you can go out and sign up for that on the first link. So if you just want to play around with it, we have lots of guides and kind of pre-dumped data sets you can play with and all sorts of things there. We also have a Neo4j Graph Academy. So if you want to learn more about our products and graphs in general, we have several different online self-paced courses on the Neo4j Graph Academy you can check out there. We also have a blog that on that third link. So you can check out things like If you want to know more about algorithms, there's blog posts about that. If you want to know more about connecting to drivers and building applications and just kind of the general Neo4j ecosystem, there's lots of content out there on the Neo4j blog. And then we also have kind of video renditions or versions of most of that content on our YouTube channel too. So if you have any questions afterward, feel free to ping me. Twitter's probably the place that I'm most reachable, but by all means, feel free to reach out and ask questions. Thank you.